Thank you. Thank you everyone for being here. It's my great pleasure to introduce Jacky for his PhD defense. As the usual protocol, we're going to, Jacky's going to be presenting first. If you have any questions for clarification, feel free to sort of interrupt or raise your hand ideally. That goes in person as well as over Zoom. And then we'll have time at the end for more discussion questions, starting off with the committee, reverse order. But for now, I'm going to hand over to Jacky.
All right. Thank you, Oliver, for the intro, and also like to thank my committee members for being here, Oliver, Max, Dave, and Shuran, and thank you all for joining. Today, I'm going to present my thesis defense on learning with structured priors for robust robot manipulation. And let's get started. The high-level motivation for all of our work is that one day we want robots to assist humans in everyday scenarios, such as homes, offices, grocery stores, hospitals, and so on. And if we look at the very high level, this robot architecture, what it might look like could be something like this. So for example, the robot could perceive the world in some fashion. Maybe that's through a camera for vision or tactile sensing for touch. And then given a particular task, the robot needs to plan some actions to complete that task and perform that action on the physical world to impart some physical changes. And really, whatever system that we design or build or deploy should have some degree of robustness. And by robustness here, I just mean that it needs to be able to handle or adapt to different unforeseen scenarios. So things like novel objects, novel scenes, novel tasks, and so on. And given these novel things, scenarios, the robot should be able to deal with these, handle these cases without too much costly adaptations. So how do we actually get this degree of generalization and robustness? Well, one thing that has been very successful in recent years is data-driven learning or machine learning type approaches. And this thesis really looks like how can we apply advances in machine learning to robot manipulation. And the way we're going to do this is by leveraging the structure of robot manipulation in robot learning. And by structure, I just mean thinking about what are the things that are special or specific about manipulation, and how can we incorporate those insights in either the design of learning algorithms or how we use those learning algorithms. So for example, some types of structure could be sort of data generating process for physical interactions, could be thinking about contacts, could be the fact that robotics needs to operate in the physical world, so it needs to obey physical constraints. So incorporating these ideas into our learning-based systems. So for our thesis work, we've sort of tackled this high-level theme from two different angles. One angle is from the perception side, and this is mostly reasoning about contacts in our perception systems. Manipulation, at the end of the day, most of the time, we're trying to impart physical change through physical contact. And so being able to sense contact, reason about contacts is very useful to get this robustness to partial observations from vision. Another angle that we tackled this theme from is on the action side. So on the action side, we're really trying to consider what are the ways that we can represent and express actions such that they're easy for learning and planning in this context of robot manipulation. And in this talk, I mostly focus on the action side of things and not too much on the perception side. So when we think about robot actions, there's many ways to categorize different action representations. The way I like to think about it is through these three abstraction levels. So on the lowest level, we have actuation level actions. So these are things like joint torques, joint angles, end effector poses, gains for end effector controllers, and so forth. They are called actuation level because they're very close to the robot actuators, and they're very, very flexible. And by that, I just mean that any physical behavior the robot can accomplish, these action spaces should, in theory, be able to express them. The downside of this expressivity is that it is, relatively speaking, a little harder to learn and do planning in because there's so many possible possibilities. If we move up one step on this abstraction ladder, we get to trajectory level actions. So think about things like dynamic movement primitives or Riemannian motion policies, basically representations that represent an entire robot motion or robot trajectory, either that's the motion for a robot arm, or it could just be the motion for the robot end effector. And in these cases, they do reason about an entire motion. So now you could perform like transformations on the entire motion at the same time instead of doing step-by-step actions. And so they incorporate a little bit more geometric structure into our action representations. The limitation for these types of representations is that they lack this explicit structure of robot-object interactions. And what I mean by that is just, if you give me a history of robot joint angles, for example, it's very hard for me to tell you what the robot is actually doing. How is it interacting with the outside world? What type of objects is it interacting with? How is it imparting that physical change? So that makes learning and exploration in these spaces a little bit more challenging. If we go up another level of abstraction level, we get to skill level action representations. So things like pick and place or flinging a piece of cloth, where the parameters of these actions have a bit more semantic information. So for example, for pick and place, it could be the picking and placing poses for objects. For flinging, it could be the grasp points from which we flip a piece of cloth. So these parameters tell us a bit more about how the robot is actually interacting with the world, and that makes them easier to learn, easier to plan with. But obviously, they're not as expressive, right? We wouldn't expect a pick and place skill to be able to, say, pour liquid from a cup. So this is sort of like the high-level context I could think about robot actions. And in the rest of this talk, I'll look at some case studies on how I approach structured actions for robot manipulation. And really, we want to find action spaces that are both expressive and convenient for actions. And this will allow us to improve the robustness, the generalization abilities, and how efficiently we can learn with these types of actions. And there's 3 examples I'll go through. The first work is more focused on learning low-level manipulation skills. And in this work, we'll talk about how we can do reinforcement learning with object-centric controllers instead of robot-centric controllers. In the next work, we'll talk about how to plan more contact-rich tasks with hybrid force-velocity controllers to represent these more contact-rich motions. And then finally, we'll talk about a work that's more on the high-level task planning side instead of low-level skills. And here we'll actually just use code as the action space for a high-level task planner. And we'll begin by talking about the first work, object-centric controllers. And this comes from the paper Learning to Compose Hierarchical Object-Centric Controllers for Robotic Manipulation. This is joint work with Mohit, Alan, Alex, and Oliver. The high-level motivation for this work is that we want to learn these low-level manipulation skills efficiently and have them generalize over different scenarios. And sort of the observations that we made is that for a lot of manipulation tasks, they sort of have these 2 properties. The first property is that we are executing multiple concurrent controllers at the same time. And the second property is that controllers tend to be executed in an object-centric fashion. So for example, for this screwing a screwdriver with a screw task, there are perhaps 2 phases. The first phase, we are reaching and aligning with the screwdriver. The second phase, we're pushing into the screw and rotating around the screw. And in both of these cases, we're executing multiple concurrent controllers. And these controllers are performed with respect to actual objects in the scene, right? Not just like random points in space. So knowing that this is true for a lot of manipulation tasks, how can we incorporate this sort of intuition about manipulation actions into perhaps a reinforcement learning paradigm that can help us improve the exploration and generalization for these learned manipulation policies? There's a lot of related works that sort of touch upon these ideas, and most of them are in this context of task frames. So basically the idea of expressing your controllers in coordinate frames that are more convenient for a particular task. We have a lot of classical works in this area that does like manually specifying more robot-centric task frames. And for some more recent work on learning with these task frames from human demonstrations. But for us, we wanted to sort of learn the appropriate task frames, so to speak, and make them more object-centric so they can just generalize with respect to objects. And as far as for composing different controllers, there's a lot of literature on this, on the theme of hierarchical controller compositions. So that's for executing multiple controllers in parallel. But these task works are also more on the robot-centric side. And the priority order from which we compose these controllers tend to be manually specified instead of learned for a particular task. Lastly, we also do have works that explore more structured action spaces for RL for robot manipulation, but these are also exploring more robot-centric actions instead of object-centric actions. So in our method, what we're doing, we're calling it RL with hierarchical object-centric controllers. And the way this works is as follows. We have some RL policy in the middle. The input to this policy is the state of the world, so maybe the poses of objects, key points on these objects, and also a list of controllers the policy can choose from. Then for the action space, the policy outputs an ordered list of controllers that it wants to execute at the same time. This list is ordered, so there's some controller that has higher priority than others. And we compose these controllers using null space projection, which is a common method for combining different controllers in manipulation. And finally, for the combined controller, we execute that on the real robot for a fixed number of time steps. We then collect new observations and rerun the loop again. So to give a bit more details on how we actually perform controller composition, I'll give an example here for composing force position controllers. So given this a set of simple object-centric controllers in this toy task, where basically the green block is, think of it as a robot, is trying to push this larger red block up and over the gray walls. Just for example, we may pre-specify some controllers that are like this. Two of them are force controllers in purple and two are position controllers in gold. And say the RL policy, given the setup, picks these two particular controllers, where the force controller has a higher priority one than the position controller with a lower priority two in the gold color. And what we do is we combine these with null space projection. We simply take the command of the lower priority controllers and project it onto the null space of the higher priority controllers, just to make sure that we always execute what the higher priority controllers want. And in that null space, we have some room to execute the lower priority controllers. And finally, we obtain the combined target, and that's the target that we execute on the robot. This is an example in 2D. We do something similar for 3D, and we'll also do something similar for rotation and torque controllers. Actually, before it goes this slide, one more point. This way of combining controllers, as you can imagine, is highly combinatorial in nature, right? If I give you like a large set of controllers, you have to choose from them. There's just a lot of possibilities to choose from if you form like a discrete action space. So instead of doing a discrete action space, we do something called an expanded MTP. I won't go into too much detail here, but happy to talk about it after the talk. But basically, we allow the policy to choose one controller at a time instead of the entire combination at a time. And that helps us to resolve some of the combinatorial action space problems. So for experiments, we tested this approach on 4 different domains. And the domain that I'll talk about in this talk is Franka hex screw task. And for all these domains, we trained these policies in simulation with PPO in Isaac Gym. And with Isaac Gym, it's great because we can simulate about 100 parallel robots on just one computer. And these policies take about 10 hours to learn. And really for experiments, we wanted to ask, does combining object-centric controllers lead to more efficient task learning and also allow us to generalize better to novel task scenarios? So for the Franka hex screw task, the goal here is for the Franka to turn and screw this hex screw with the hex key. And in order to do this task, the robot needs to push and turn at the same time. If you just turn without pushing, that won't actually make any change to the key. To the screw. And for the train and test split here, we are dividing them based on the size of the key and screw pairs. So for the training test, for the training set is a narrower range of these sizes. Those are like scale multipliers. Test has a broader range of the scales. The different approaches that we compare against are these 4. So expanded MDP, that's our approach where we allow the policy to choose one controller at a time in order to find multiple controllers to execute at the same time. Combo means having this large discrete action space for the policy to choose from. One controller is we only allow the policy to run one controller at a time instead of multiple controllers. And end effector space is doing RL directly in end effector space and not using our controller setup. So here's the training curve, success rate during training. And the main comparison here really is that between our approach and the approach that just does exploration in end effector space. For this particular task, it's very, very hard to explore because there's a lot of constraints. You need to make contact with the screw first. You need to obey perform like the pressing and turning motions at the same time. And so it's very hard to do random exploration in end effector space and get useful training signals. Whereas if you do object-centric controllers, you're more likely to stumble upon successful behaviors. So that's the case for more efficient learning for these manipulation tasks. For generalization, we tested our approach on some test set again, and also on the real world setup. And we see that our method sees its performance degrade a lot less than the other comparisons. So takeaway from this project, here the structure action space that we're using is this composition of hierarchical object-centric controllers for reinforcement learning of low-level manipulation skills. And this allows us to improve exploration for task learning and also allows us to get a bit better generalization behavior to novel scenarios. So the next work I'll talk about is planning with preconditions of hybrid force velocity controllers for contact-rich manipulation. And this comes from the work learning preconditions of hybrid force velocity controllers for contact-rich manipulation. This is joint work with Sanyi and Oliver. The high-level motivation for this task is, for this work is how do we actually plan and perform more contact-rich tasks in everyday scenarios like shelves and cabinets. And in general, we call these more constrained environments because there's a lot of things that are basically in the way, both occluding your vision pipelines and also occluding your actions. You can't just literally grasp all the objects. And that means we have to use diverse non-prehensile behaviors in order to manipulate objects, such as sliding, pivoting, toppling, and then pushing. And if we compare this to the prior approach, instead of specifying all the object-centric controllers by hand, what we're doing here is just have one very expressive low-level action representation, and that's the hybrid force velocity controller. And we'll show how that one representation can perform and exhibit all of these different types of non-prehensile behaviors. Another thing I like to note is that contact-rich skills are prone to failure. What that means is that because a lot of these works, especially in prior works, require precise object pose feedback. And it's very hard to obtain this in a more realistic scenario, especially in constrained environments and especially during robot-object interaction. So here what we do is that we make some approximations and we need to learn when these controllers would be successful and when they will not be successful due to these approximation errors. And we call that function precondition. And this is the thing that we learn in this work. And finally, we need a way to plan with both non-prehensile and prehensile behaviors. And that's because if the object is not occluded in a particular scenario, we should be able to just do pick and place or planning non-prehensile behaviors to enable pick and place in later stages. And to do that, this work is gonna focus more on high level skill planning instead of low level skill learning. There's a lot of related works in this area about non-prehensile manipulation, ranging from more model-based approaches to model-free methods. There's also a breadth of work on pre-grasp manipulation, and that's just trying to singulate some objects or pushing and sliding objects to reveal a grasp for a downstream task. The limitations for a lot of these approaches is that they make strict requirements on object modeling. So you need to know the exact object geometry beforehand or object pose, or maybe all the objects have the same geometry, for example. And again, a lot of these works need object feedback during execution, and they typically cannot sequence multiple types of non-prehensile behaviors, right? They might just have one controller that just does pushing or just does sliding, but they can't plan, okay, let's push first, then slide, and then do a pick and place, for example. So at a very high level, our approach looks something like this. The task that we're concerned about is rigid object manipulation in this shelf environment. The input to our high-level system is a partial point cloud. And the output is hybrid force velocity controllers. That's our structured action representation. And I'll spend this slide talk a little bit about HFVCs. So in HFVCs, you have two controllers. One is the force controller, and the goal of the force controller is to maintain contact with the object. And the other controller is a velocity controller, and that's just trying to achieve the actual motion that you want. And we have existing HFVC solvers that can turn this state parameter tuple into force and velocity commands. And by state, I just mean the current object pose, and the parameter is the delta subgo pose, basically where we want the object to go to, as well as the initial robot object contact point. So we have some methods that if you just give it these two things, it will try to compute what the force velocity commands are. Yes, Dave?
The HFVC is not the thing you presented in the previous project, or is it related somehow?
It is related in a sense. In the previous project, there's also a combination of different controllers, but that was more like you have to manually specify a lot of different controllers, where this is like it solves for the force velocity commands.
Okay.
Yeah.
It's similar in just that it's a hybrid controller, but it's otherwise different, I guess.
Yeah, it's just the controllers here are you solve for it instead of manually specifying.
Yeah, okay.
Yeah. And the goal for the HFVC solver is to move the object to that desired subgo pose. And in our experiments, we run this about 20 hertz. To make this a bit more concrete, what are these sub-goal delta poses? Here's some examples of that. So on the left-hand side, those are like planar delta poses, like offsets in translation and rotation. And then here we have some examples of delta poses that have different stable poses. And for robot object contact points, we just sample on like a grid on the robot surface. And again, given these two things, the goal is for the robot to move this object according to the parameters. So in order to execute HFVCs on a real robot, we need to relax some requirements from prior works. And in particular, prior works typically need us to provide an initial feasible trajectory for the controller to follow. And this is usually done manually, or you can run a simulation to obtain what the feasible trajectory looks like. And also they require closed loop object pose feedback. So instead, we need to approximate these things. So we just interpolate a linear trajectory instead of having like a feasible trajectory. The linear trajectory may not be feasible. And we also estimate the object pose from proprioception by just assuming that the robot object contact point is static. So if it's static, then depending on where the end effector is, you can sort of guess where the object is. And because these approximations are definitely not correct all the time, not all executions are going to be successful. And actually in simulation, we got a 50% success rate here. And by success rate, it just means that an execution is successful if at the end, the object is close to the subgoal and is in a stable pose. And this, again, the failures are caused by modeling mismatches, and this motivates us to learn what we call a precondition function, which helps us to filter out the successful actions and the unsuccessful actions. And before moving on, just like to show some videos of running HFVCs on the real robot, and just to show you that it can achieve diverse motions like sliding, pivoting, toppling, and pushing. And so this is all done with just the same controller implementation, but you provide it with different parameters and it can solve for different actions. So I'll spend this slide talking a little bit about the precondition learning aspect. It's trying to predict, given this the input to the HFVC solver, which is the state and parameter tuple, will this execution be successful? And the state representation here, we're taking in the segmented partial point clouds of the scene. So that means we don't have to have access to the actual object geometries, and the parameter against the delta object pose and the initial robot object contact point. We trained this model in simulation by randomizing the object and shelf geometries for some objects from MyCB. And we also randomized the sizes and poses and sample a whole bunch of different initial state and parameters. And the performance we get is about 80% classification accuracy, which is not perfect, but it's actually good enough for us to start doing some planning. And the architecture sort of looks like this, where the model first takes in a point cloud of the scene and it's using pointnet++ to process that point cloud. And after a few layers of feature extraction, we just do a classification at the very end. What do we do once we have this thing that tells us whether or not an action is successful? Well, we can use it in a search-based task planning framework. So just to reiterate, the task here is we're in the shelf domain, and it's defined. Each task is defined by a start and go object pose, and these poses don't have to be in the same stable pose. And the planner has access to two skills: the HFVC skill, which is a non-prehensile skill, and a pick and place skill, and that allows us to do pick and place when the objects are not occluded. The planner looks something like this. We have a planning graph, and in this graph, each node is a state, and which is just the current object pose. Each edge corresponds to an action, which is a skill parameter tuple. The parameter for the pick and place skill is the pick and place poses for the object. And so we have this graph, and we pick basically during task planning, we need to pick which node to expand via some priorities. We have a heuristic function to choose that. And then at the end, we need a way to get the successors of performing, acting in a particular state. And to get successors, there's three things that we need. One is having this parameter generator, which basically tells us the entire set of possible actions to perform at any given point in this graph. And here, this is basically a scripted, discretized set of actions. You can sort of think of this as like motion primitives, but more for objects instead of for the robot. And then we need a precondition function to perform filtering for our actions, and this is learned. And then finally, we need a way to record the effects of performing an action. And in our case, this is just a sub-goal delta pose that comes from the parameters for each skill. And we're basically just saying that if we think the precondition is successful, then the object should end up where the parameter told it to go. So quick summary of our approach. We are trying to move an object from a start to a goal pose in the shelf domain. We allow the planner to replan, and we use a learn precondition to filter HFBC skills. So in the beginning, we have a point cloud. We have a visual perception module that helps us perform segmentation and extract some bounding boxes. The bounding boxes are used by our parameter generator for collision detection, but that's about it. And then all of this, the generated parameters and the segmented point cloud goes into our precondition model, which helps us to filter those actions. And then we have a task planner that uses those filtered actions. And then we run the planner with a given planning budget. And once the planning budget exhausts, we execute the first action of the best plan found so far. And after that execution, if the object doesn't actually go where we think it should go, then we replan again. So here I'd like to present some quantitative results, and all of these are evaluated on test objects for the precondition functions not seen during training. There's basically 3 baselines that we compare against. One is no PC, so this is not using the precondition function, and this is like the main comparison, like what does learning the precondition function get us? And then another baseline is for only doing pick and place, so not using the non-prehensile skill, and then finally not doing any replanning. And so the main comparisons between ours and no PC, and you can see with our approach, we get about a 73% success rate. If you don't use the precondition, you get about a 51% success rate. So that shows the benefit of using the learned precondition model. If you just use pick and place, we get a 27% success rate. And that just means about a quarter of the time the initially sampled start and goal poses are not near the shelf walls. And also replanning helps a lot in our case.
Do you have a metric for how correct your prediction model is? Like how often does it correctly predict that the top or the vertical work?
Yeah, it's 80% accuracy.
Okay.
Yeah, and it's also about 80% precision and recall. And now I'd like to show some videos of running this in person simulation than in the real world. Here the goal is trying to get that object from the right side of the shelf to the left side at a different stable pose. So the planner first slides the object to create a grasp, then it performs that pick and place, and then finally pushes the object into the goal pose. The next video is somewhat similar, but because this object is wide, it needs to do a grasp, like a vertical grasp. So it slides the object from the side instead of the top. And then it places the object into a pose that's close to the corner, and then does like a pushing and a pivoting motion to align the pose. And we also implemented this on our real world robot setup. So here the goal is just to get the object into the middle of the shelf. So it first pivots the object and then does this pick and place motion. And then in this case, it's trying to slide the object first and push it into the corner. This arm swing motion is just to get a point cloud of the scene. And so it's able to place the object at a different stable pose and finally push the object into the corner. So takeaways from this project is that here we're planning with preconditions of hybrid force velocity controllers, and that is the structured action space that we're using. HIVC is great because it's one controller implementation, but it's very expressive. It allows us to do all sorts of diverse contact-rich behaviors, and it's also very easy for us to do planning in. The execution of HIVCs on a real robot setup is not always successful, and that's why we need to learn the precondition function to help us filter these actions. And then this allows us to do all sorts of manipulation in constrained environments with the help of replanning. So that's for that work. And for the next work I'll talk about is more on the high-level task planning side instead of the low-level skill side. And here the structure action space for high-level task planning that we're going to use is actually just computer code. And this comes from the paper Code as Policies, Language Model Programs for Embodied Control. And this is joint work with a lot of folks at Google, Wenlong, Fei, Pen, Carol, Brian, Pete, and Andy. So the motivation for this work is how do we generalize manipulation planning to much more diverse tasks, right? So think things like put the blocks in a horizontal line near the top of the table, or drawing a pyramid as a triangle on the ground. And can we have actually one system that can help us plan all these different manipulation tasks? And the setting that we're operating in is that we assume that we're given some parameterized low-level skills. We're not dealing with the skills, we're just dealing with planning. And we're also given some perception APIs, perception models. And we really want is how can we string together these APIs that we're given in a more flexible way so we can support a lot of diverse tasks and output a lot of diverse policies. And in order to support flexible task planning, we need a flexible way to specify tasks. So instead of something like start and end object poses, maybe we can just use natural language to describe what that task looks like. There's a lot of recent work in this idea of just like language, combining language with robots, from directly learning language condition robot policies, or learning the semantics of sentences or the natural language descriptions and sort of mapping those to visual perceptions. The works that are more related to this work is recent works on leveraging large language models for task planning. And I'll try to explain this, what that means on this slide. So previously, if we want to learn a robot policy, it probably looks something like this. In the middle, we have our policy, could be a neural net, could be something else that's mapping perception inputs to action outputs. You can train this per task or in a multitask setting. And in some recent works, people have explored using large language models to plan. So here, the idea is that we're going to have this large language model, which maps text to text. And so the input is some natural language descriptions of perception, like where objects are or what objects do you see, and natural language descriptions of the task, maybe like clean up the table. And then the language model is going to output a sequence of natural language instructions for the robot to execute. And what do these instructions look like? Well, they could say something like move left or pick up the apple or open the drawer, for example. And the pros of this approach is that it is very expressive, right? The input is natural language, output is natural language, very expressive, very flexible. The con is that because the actions are also in natural language, it is a little hard to ground, right? You need a way to translate all of these low-level natural language actions into robot actions. That's not very straightforward to do. It's also hard to be very precise with natural language or for large language models to deal with that level of precision. So maybe you just want to move left by 1.56 meters or something. It's hard to express that in language. And it's also hard to specify more reactive behaviors with just a sequence of steps. So maybe you want to output a policy that's like go to the left door if it's blocked or something, or if the door on the right is blocked, right? So we need a way to specify these reactive behaviors. And the question is, well, we've seen some promising capabilities from large language models. Can the large language models also express these capabilities as well? And the angle that we tackle this problem in is through code generation. The thing that a lot of us know is that large language models can also write code to some extent. And so this is an example from a standard code generation benchmark. The way large language models work is that you give it a piece of text and just trying to autocomplete the rest of that text. So here we're giving it the beginning of this function that computes the Fibonacci number. And then if you put this into a large language model that's trained on code, you can try to autocomplete the rest of that function. This is something a lot of us may have experience with just in our code editors nowadays with these AI-based code autocompletion tools. And just a little bit more information on this model. For all the examples that I'll show in the rest of this talk, they're using OpenAI's codex model called Code DaVinci 002. So this is a pre-trained language model. We're not training our own language models here. And this model is trained on GitHub code, and the API is publicly available. I mean, if you want, you can go on the website right now and just try this Fibonacci example. It will be able to autocomplete that for you. So this is more generic code completion, code generation. But the way we really want is to borrow or use these capabilities for robotics and robot manipulation and get it to write more domain-specific robot code. So our approach is going to look something like this, right? We have a large language model that's still taking in natural language descriptions of the task. But what's going to happen is going to write a short snippet of code. And this code is going to call the provided perception APIs. It's going to call the provided action APIs to actually perform the task. So just to give some quick examples of what code generation looks like and how this applies to manipulation. And here, basically the way we do this is that we always have this thing called a prompt, which basically shows the language model what we want to do and how we want it to respond to our commands. So this is something that we have to write as a robot engineer. So in this prompt, the way we structure prompts is that there are two parts. The first part is what we call hints. These are things like descriptions, import statements, function signatures, the type of information that you only need to provide once. And then the next part of a prompt is what we call examples. So these are pairs of instructions and responses. So here the instructions are all formatted in comments, and the responses, we want it to be the actual code. And in here, basically, what we're telling the language model is that, hey, when you compute a response, I want you to save it to a variable called return_val. This is important because when we execute the actual responses, we'll just look for what the value for that particular variable is, and that's how we get the results back. And another thing that's important about this prompt is that it shows the language model what we mean by going to the right and going to the top. Right? So going to the right is positive X, going to the top is positive Y. So that's how we specify cardinal directions. With this very short prompt, you can already get it to do tasks that are slightly non-trivial. So here you can ask the language model to get the leftmost points in a collection of points. By the way, so all the green lines are instructions, and all the blue lines will be responses from the language model. So here it calls np.argmin and chooses the correct dimension for left and right. Get the center of a collection of points. And getting the closest point to a collection of points. One thing I like to highlight is in all of these responses is calling NumPy APIs like argmin, mean, linealgebra.norm that are not present in the prompt. And this is possible because in the training data, this model has seen a lot of NumPy examples because it's a very popular third-party library. So in these cases, you don't have to really demonstrate what are all the available APIs. That's just part of its training data that it can understand. But perhaps what's more exciting is that we can get the language model to leverage first-party APIs. So here in this prompt, we show two first-party APIs. One's called getPosition, one's called putFirstOnSecond, and getPosition is a perception API that gives you the coordinates of an object by its name. And this is using a neural network to do that. And the putFirstOnSecond is a scripted pick-and-place primitive that uses a suction cup to pick and place objects by their name. And so in the prompt here, we give two examples of how to use these APIs. And again, with this very short prompt, you can get it to perform new tasks. So the first task is move the red block a bit to the right. And it generates a piece of code that moves the red block to the right by 5 centimeters. This is great because in the prompt, we only showed what it means to go to the left. And so it's able to know that what left and right means. And because we said a bit, it's the magnitude is also smaller than sort of default magnitude that has seen in the prompt. We can also leverage the language model's ability to do some sort of natural language-based reasoning. So here the instruction is put the blue block on the bowl with the same color. So we didn't have to specify exactly what that color is. It's able to do some sort of these types of simple language-based reasoning tasks. There's two additional things that we do in this work that really allows us to handle more complex tasks. The first thing that we do is something we call prompt composition. And that what this is basically allowing us to combine multiple different prompts that are specialized in performing different functions and composing them just with function calls. So here the instruction is very complicated. Sorry, do you have a question?
Here's a question.
I think we can address the question at the end.
Okay. Okay, cool. So the instruction is while there are fruits with area bigger than some threshold that are left of the red bowl, move them to the right. So this is the code that it generates. There's a while loop in there, there's a for loop in there. So that's another advantage of using code is it's able to leverage these classical logic structures. But here you'll notice that it's calling this function called parseObject with a natural language description. So this is a function that's actually just implemented by another prompt and language model. And the whole goal of that parseObject prompt is just to reason about object names based on natural language descriptions. And so basically we pass that to a parseObject prompt, and here is the code that it generates. And this is an example of what we call prompt composition. So this is great because we know that language models only really work well when the prompts are more specialized. If you add a lot of different capabilities to the same prompt, it gets confused. There's also a limited window for how many examples that you can put in a prompt. So this way it really allows us to build out more complex applications. The next very important thing that we do is what we call hierarchical code generation. So if you look at this code that it generates, it's calling a function that doesn't exist, right? So this function is called get objects bigger than a particular area threshold. This is not a first-party API that we provide. It's also not a well-known third-party library. And we allow the language model to do this because at runtime, what we do is we'll parse the generated code, figure out which functions haven't been defined yet, and recursively call the language model to define those functions for us. So here's what that looks like. And here again is calling a function that doesn't exist, which is computing the bounding box area for an object. So we recursively call a language model to generate that function. And it finally generates a function that we can actually run, where it calls getting the object bounding box API, which we do provide. And that's what we refer to when we say hierarchical code generation. So in summary for this work, we're using natural language instructions and converting that to task policy code using these large language models. And this code will able to use perception outputs to inform action. So it's more reactive that way. And of course, this means that we as the robotics engineers need to provide the actual perception and action APIs. So it's more on the high level planning side. The benefit of this approach is that it's very expressive. Input is code, input is language, output is code. This gives us a lot of flexibility. We can perform precise numerical computations, for example, using NumPy, something that large language models would struggle to do just by themselves. This allows us to solve diverse tasks with few-shot prompting. And we actually inherit all the benefits of large language models, such as supporting multiple languages, reasoning about context. I'll show some examples of this in later slides. Yeah.
So you might actually be able to answer the question.
Oh, really?
Okay.
Sorry, what's the
You go to the chat. Sorry.
Yeah, the chat is on a different window.
Why does code generation run into the same problems as the recent meta science writing LLM Galactica, which looked like science writing was not usually correct?
Yeah, that's a great question. Beyond just inheriting the benefits of large language models, we also inherit all the limitations of large language models. So there's a lot of concerns about the robustness of these outputs, whether or not you can make any guarantees. At this point, I don't think we have good research or tools on that side, so I would not recommend putting this on a real production robot. But I think one thing that is in favor of code generation is that comparing to natural language, code tends to be a bit more logically consistent. And this is something we've observed. If you try to write something like this, but have it output natural language, it will perform worse than if you let it write pseudocode. So if you let it write pseudocode, it actually it's more correct more of the time. This is not part of the paper, just like this will be experienced. And that's actually what motivated us to switch all the way to code, because we saw it was performing really well with pseudocode. Why not just use code? So here I give some examples of sort of benchmarking this entire system in simulation. And in simulation, we're only evaluating a subset of all the potential instructions this method can support, because you have to somehow write a way to be able to evaluate the ground truth success and provide ground truth demonstrations for our baselines. And this is just really hard to do with a variety of instructions. But we do some instructions, like, for example, put the pink block a little bit to the bottom of the gray bow, or put the pink block at the corner closest to the cyan bow, right? So like basically instructions that require some amount of both natural language reasoning and also spatial geometric reasoning. And here what we're evaluating against is a clipboard, which is a method that does imitation learning that maps directly natural language instructions to robot actions, and also sort of a natural language planner. So that's like just planning with natural language and not using code as the output. We'll see that for scene objects and scene instructions, this is basically the training set. The performance is comparable, but for unseen objects and scene instructions, or unseen objects and unseen instructions, the performance of our method degrades a lot less than the alternatives. But I do have to know, like, it's not 100%, right? It doesn't magically solve everything. but we do get a bit better generalization abilities. So in the remaining part of this project, I'll give some real world examples of actually applying our system to a wide variety of manipulation task domains. And the way this works is that the perception APIs that we provide come from what we call these visual language models, like open vocabulary object detectors like VILE or MDETR. And then for action APIs, we have just a lot of scripted actions basically for doing pick and place, for example. And for all of these tabletop manipulation domains, we have 5 different prompts that we try to compose with each other. The high-level UI has the most number of examples in the prompt, there's about 35 of them. Parse object names, parse position names, these have like 10 examples each. We have a parse questions that allows the robot to basically converse with the human and answer basic questions like how many blocks are left of the red bow or something like that. But I don't actually have video examples of that. But that is one thing that we support. And finally, for function generation, we have 7 examples of how to do that. So here's a slide on tabletop manipulation that's more about reasoning about spatial relationships and shapes and contexts. So here the instruction is put the red block to the left of the rightmost bow. And then the next instruction is move it to the side farthest away from it. So this is an example of reasoning about context. It needs to know what it means in this context by referring to the previous command. And we're going to say put the blocks in bows with non-matching colors. So in the prompt, it has seen an example of putting the blocks in matching colors. And we can also sort of combine these more precise spatial descriptions, like put the blocks in a vertical line, 20 centimeters long and 10 centimeters below the blue bow. A lot of this reasoning is just done via using the NumPy library. We can also do some shape manipulation. So here, the first command is arrange the blocks in a square around the middle. And for these shape manipulation tasks, it's using the library Shapely. It's a Python library that allows us to create and manipulate shapes. And we have another, the next command is make the square bigger. So again, sort of reasoning about context. And this transformation is actually writing a code to do like scaling transformations in NumPy. You can say something like undo that, so I'll undo the last action. So still reasoning about context. We can also write some rotation code, like rotate the square by 45 degrees. So here I implemented a NumPy function that forms the rotation matrix and is rotating these waypoints for the objects. We can do something a bit more fun. So here is sort of a task where we're trying to separate different object categories. The instruction is move all fruits to the green plate and bottles to the blue plate. And here's some more non-trivial uses of the perception API. So move the smallest fruit back to the yellow plate. So that's using like the bounding box API again. We can generate while loops, wait until you see an egg and put it in the green plate. And put the darkest object in the plate that has the apple. And finally, I'd like to show this demo with our system on a mobile robot platform. And here what's happening is in the beginning, the user is teleoperating the robot to 3 different waypoints and telling the robot where the recycle bin is, where the landfill bin is, and where the trash recycle, landfill, and compost bin, there we go, are. And then we tell the robot to put away the Coke can and the apple. And because it's a large language model that can do language-based reasoning, it correctly chooses the recycle bin for the Coke can and the compost bin for the apple. So this is sort of an example of the advantages of combining language-based reasoning with code generation. Like you could perfectly have a code generation model that just writes code, but doesn't do language-based reasoning, but you wouldn't be able to do something like this. So here I'll spend a slide talking about limitations because there are definitely limitations. So one is that right now we're not providing perceptual feedback to the language model. We're providing that feedback to the code, but not to the language model itself. Why is this useful? Well, so here is actually an example of the language model generating a piece of code that can balance the OpenAI card pull. And the reason this works is that the controller gains that it picked immediately just sort of worked. It got lucky. If it doesn't work, you can imagine having a system that looks at what this robot is doing, how it's performing the task, mapping that description back to the language model and have the language model able to iterate on the code that it generates or fix bugs or improve the performance of the generated policy. So that's something that we're not doing at the moment, which I also think is very important for these more low-level continuous control type of tasks. We're obviously limited by the perception and action APIs that we provide, right? If you don't give it an API that can fold a piece of cloth, it's just not going to be able to do that. There's a thing that we observe that we call prompt saturation. So basically, your prompt can't get too long. If it gets too long, even before hitting the actual limit, it will start to forget the earlier parts of the prompt. So that is definitely sort of a limitation against like very complicated tasks. Obviously, we do have to do prompt engineering. Basically, you can think of this as instead of doing data engineering for typical machine learning tasks, you're just putting that effort now on prompt engineering. I think a big limitation is actually right now it's hard to tell if an instruction is feasible or not without running it. Even now, like if you give me a new instruction, I can't tell you with confidence like that will definitely work on the language model or not. I just have to run it and see it. And as I mentioned, we do inherit all the limitations of large language models as well. So some promising future work in this area, one is just giving more feedback to the language model, and we've seen some works that do that. And I think especially with these more text to whatever generative models, that could provide a meaningful signal to ground feedback. So like text to image, text to video, for example. There's a lot of exciting works in retrieval-based methods. So that could be one way to get around the prompt saturation problem, giving the language model ability to index into a database or a larger corpus of instructions or examples, not just in the prompt. And finally, an ability for the language model to maintain some external sense of state I think would be very useful. So allowing the language model to have a scratch pad essentially and writing to that and both reading from that. So again, just reducing the limitation on the prompt size. So takeaways from code as policies, the structured action that we're using here for high-level task planning is just code. And this code we generate uses given perception and action APIs, enables us to do precise numerical reasoning that is very hard for language models to do by themselves. Hierarchical code generation does improve code generation performance a lot. I didn't include any quantitative results in that, but I can show it to you during questions. And we can do these diverse tasks with few-shot prompting. So that wraps up all of the works that I'll talk about during this presentation. And really, again, the summary here is that we are looking at structured actions that are both expressive and convenient for manipulation. For low-level skills, we explored object-centered controllers and hybrid force velocity controllers. And for high-level task planning, we showed how code can actually enable us to plan very diverse tasks with not as much effort. I'd like to spend a slide talking about sort of the future outlook for robot manipulation. And again, I think for me, the motivation here is we want algorithms or systems that can quickly and cheaply adapt to new scenes and tasks. And something I'm interested in is just trying to explore beyond this sort of static manipulation that I've been doing in all of these works towards more, say, mobile manipulation or manipulation with an entire robot body. So a lot of these things are just done with the robot end effectors. But there's no reason why that has to be the case. You can manipulate with the entire hand, the entire robot arm, multiple arms, for example. And how do we do all of this in a more open world setting? I think there's definitely a lot of open questions there. For these low-level skills, I do still think we definitely need to explore better action representations. For example, if I want to have a system where I have 2 arms, 2 dexterous hands doing some task, I don't really have a good answer to like what is a good action representation for that scenario. I think if you just explore in joint angles or joint torques, it's just going to be way too inefficient, but there needs to be some high level of abstraction for these more complicated low-level skills. And for high-level skill planning, I'm very optimistic about using large language model and code to play a part in that moving forward, especially for human robot interactions. And but by themselves is probably not enough. You probably need some way to maintain external state. And maybe also apply this to some existing algorithms in TEMP, task and motion planning, maybe bring some of the more open world capabilities of large language models into these more structured algorithms. And finally, I'd like to throw in a comment about robot learning. So machine learning or learning in general is about data, and robot learning is about generating interaction data. And unfortunately, robot interaction data is very expensive to collect if you compare it to things like images or text, which you can just download off the internet. We definitely need better ways to generate more scalable ways of generating robot interaction data, like meaningful physical interactions. There's been a lot of exciting work in this area, and I think that's also worth future explorations. Finally, I'd like to wrap up by thanking my advisors, Oliver and Max, as well as my committee, and also all the collaborators that I've worked with in the past, both from CMU and also my collaborators at Google. Research is not done alone, and I really appreciate everybody's support and guidance throughout these years. And finally, I also like to thank all the friends and my peers at the Robotics Institute. I think for me, a place is really just about its people. And I think it's really the RI family that made my PhD work. So thank you, everybody. And that is the talk. Happy to take questions.
Right. So we'll go to the committee. There is one more question in the chat. It's a sort of small one. Are some computer languages better or worse for this? You use Python. What about C or C++? What about special purpose robot programming languages? What about very high level languages?
Yeah, so Python works best for that particular model because I think Python is just a lot more, there's just a lot more examples of Python in the database that was used to train Codex, which is the model that we used. I think for Google's models, like they were probably using something that's not primarily Python. So I think it does depend on the data that the language model was trained on.
All right, so we're going to hand over to the committee. So Sharon, would you like to start us off?
Okay, cool. I'll ask the first special question. Hi, Jacky, really nice presentation. First, I think a relatively simple but also high level question. So your talk has two parts, right? First is all about low level controls, and the second part is like the high level code as policy stuff. And have you thought about like how you can like combine them, or for example, more concretely, how you use methods like code as policy for context-rich manipulation instead of just pick and place?
Yeah, I think there's two ways to go about this. One is from just like these low-level controllers aspect, and one is from the code as policies aspect. So I think with code as policies, I think in similar approaches, I think we're in a very interesting setting where now we might need to ask the questions, how do we design the low-level skills or parameterize the low-level skills so it's easy for the language model to use? So thinking about the appropriate action spaces, not for like PPO or something, but for a code writing language model. I think that's an interesting question. What are the right parameters, basically the function arguments that go into this? At what abstraction level do you define these actions? I think there's a lot of opportunities there. And then if we actually want the language model to write more of these context-rich controllers, I think what you really need is that feedback loop, because this is an area where like grounding in the physical realities of robot world object interaction is just becomes a lot more important, which I don't think is really captured by text data alone. And I think that this is an area where, again, the generative models may come into play. So text to motion, text to video, maybe you can do video to text one day. Maybe you could do these more multimodal language models where you pass in the video, you pass in like a question, and maybe it can answer something about that video. So for example, is the car pull like leaning left or right? Is it pushing the object too hard? Is the object moving fast enough or something like that? So basically able to provide natural language descriptions of what you're actually seeing, and then giving that feedback to language model so then it can actually iterate and improve on these low-level continuous controllers. I think that's going to be very important if you want to get that to work.
Yeah, I guess when I asked the question, I was mostly thinking about things like context or forces is something that we don't really describe in language as much. I was just thinking whether like things like code as policy or language model even will play a role, or what do you think? Like, do you think that it's going to be helpful eventually, or it's kind of like conjunctural that is not particularly related?
Yeah, I think it depends on a lot on the data. So let me think. So there's going to be a lot of less data just describing like forceful physics in whatever data set it was trained on. And I think if you think about it, there are definitely things that CODIS policies can't do that's a bit more obvious for us to agree about. It's like it probably like I can't just do object recognition, right? The way we've been doing that is through neural networks, and that's not written in code anywhere, so it's not going to be able to do things like that. Maybe what you could do is have it write the right optimization objectives or the optimization constraints or functions for you to actually learn something or optimize for something instead of actually describing the actual solution to these forceful interactions. I think that's probably a better way to go about it.
Cool. Yeah, I think that's a good idea. Another question, follow up on that, is I think another limitation that I see about like CODIS policy potentially is the system actually does not improve over time, or it's more interactions with the environment. That's kind of like going against with this whole general idea of learning, right? So for example, you ask your large language model to write the code and you execute it, and if it doesn't work, you don't know how to improve it. Or if it works 50% of the time, it cannot learn from the interactions. Have you thought about how we can like make the system able to improve over time or make use of the data?
Yeah, I think there's two things you can do, and we've seen examples of this just like outside of robotics. One is I think it's called like reinforcement learning with human feedback. Just something people have been doing for language models. Basically, having either a human demonstrate, not demonstrator, like humans labeling like this response is good or this response is bad, and using that as to label data directly, or people who have been training reward function models that try to model what the human preferences are, and then using that to do RL for the language model. So I think that's something you could definitely do with robotics for a lot of these manipulation tasks. Just have it execute a bunch of commands, generate a bunch of commands, and then just have a human rate a subset of these, and then learn some reward function to label the rest, and then just use that in a loop. I think that's definitely possible. And another one with continued learning is some of these things are not necessarily performance related, is more just like the language model doesn't have enough information. Like maybe the particular human user always prefers, I don't know, like the fork to be on the right side of the plate or on the left, things like that, human preferences. So I think, yeah, there's a lot of opportunities here to use more retrieval based methods that can have like an external storage for a lot of these things that you don't need to fine tune a model for, but it's more like one-off information that you can query and retrieve. So I think there's probably some opportunities there as well.
Cool, thank you. Yeah, that's all my question.
Thank you, Sharon.
Okay, thank you. Should I go over to Dave?
Sure. Oh yeah, great talk. I'll start with the first project. So I guess for this task, I was trying to get into the sense of what the priority would be between different controllers. So if you have this task where one controller is force and one's position, like would the force controller usually would have higher priority, or how does this work?
If your force position controllers are convenient enough, then it's usually the force controller that has higher priority. Because you want to maintain contact. Like once you lose contact, it's you have to sort of start over for this task at least. Yeah.
Right. So I guess like would like sort of heuristics work for choosing the priority, or does this need to be learned?
Yeah, I think learning makes it a bit more flexible because we just enumerated a whole bunch of controllers. They're very simple, like one-dimensional controllers. We didn't really like design them too much in that sense, so you don't have to put as much like domain knowledge in every single domain that you have. So I think that's the benefit of learning. But I think, yeah, if you just sit down and think about like, oh, for this task, what is the right controller? At least for this pushing up part, I think you can come up with a pretty good priority. I think the tricky part, let me see if I have some examples of this. Yeah, so some of these, oops. Yeah, so for this, some of these tasks, like it's not clear, like at the end to get the object over the edge, like what controller you would be using. So I think in those cases, it's easier if it's learned.
Yeah, it might be cool to like kind of visualize what priority it's picking at each time step or whatever.
Yeah. We have some plots like that in the paper, but it's really messy to look at.
Maybe like a video, you like overlay with this,
I
with
see.
like bar graphs of like what
I see.
priority or something. Yeah,
Okay.
anyway, it's cool. For the second project, I'm curious, what's the planning time and what's the bottleneck in terms of planning?
Yeah.
Oh,
So,
yeah, you have this here.
so the bottleneck in terms of planning is actually, so each time we run the precondition function, it needs a point cloud, right? So when we expand this tree, each node needs to have a point cloud that's associated with it. So most of that time is actually spent in allocating new memory for point clouds.
Allocating memory?
Yeah. Because it's like 1,000 something, more than 1,000 points or something. But that's most of, if you get rid of that, it's actually much faster.
Huh.
And I did try to optimize that a little bit. The way I actually implemented is like more of a lazy thing in the sense that we don't every time you expand a node, I don't actually copy the point cloud. I just store what the transform for that object is.
Right.
You can stack these up across like an entire path. And until my planner needs to evaluate the preconditions, I don't copy the point cloud. But it's at the end, I need to do a copy, and that's where the time comes from.
That's weird. Okay, I would not have expected that.
Yeah, the neural network inference is very fast.
Right.
That's not the problem.
Interesting. Okay. Cool. For the last project, I guess, served just like a kind of provocative philosophical question. So, I mean, how do you think humans do planning? Do we like have some kind of pseudocode that's running in the brain? Yeah, but do you think this like relates at all to humans, or do you think like we should be trying to do planning in a more like human-like way, or we should not do it in a human way, or
Yeah, that's a great question. What this tells you is that the way humans write code is a great way to do planning. It doesn't really tell you much about if that's actually how humans. I think if you want to do the way like humans do planning, I think doing that in natural language is probably a lot closer than writing code for it.
Okay. Interesting. Yeah, I actually am not sure because natural language has this issue that Sharon was asking about before, that like there are a lot of things that we don't really describe in natural language, like
Yeah.
you know, how much force to apply something or exactly where to place it. You won't see that a lot in natural language. You see like numbers a lot more in code,
Right.
which is nice, but then it's
Yeah,
also
that-
don't talk in code. So.
Yeah, they give you the more like precision aspect of
Right.
it, right? But like code is not open world in the way language is.
Yeah,
And there's a lot of details in the real world that's not written down anywhere. I think
Right.
that's where the limitation.
yeah. Okay, yeah, I'll stop there.
Max, can I ask your questions?
Yeah, sure. Great talk, Jacky. A few questions. So for the first work, I guess the overall framework, you know, for having multiple kind of controllers and having them added up to give you a resulting emerging kind of control and so on. Like this is also kind of a outside of manipulation related to more broadly behavior-based mathematics, where you have multiple vectors, force vectors, and you combine them and so on. So in the day, you know, pretty prone to getting stuck in the local minima, where the control they cancel themselves out and so on. So you know, do you see this manifesting here as well? And did you ever encounter problems along that line? And what would be the solutions to those?
Yeah, I think there's like three aspects to the solutions. One is just that because we're doing null space projections, it's not as easy as if for controllers to cancel them each other out, because you always have at least like one controller that's doing what it wants. It won't get canceled out by the other controllers. The other two parts is that the policy can choose to use no controllers, or basically like you can choose at most like 5 controllers, but we gave it the ability to choose only one controller and just don't do anything for the others. So that also reduces like the likelihood of controllers conflicting with each other. Like if it's not necessary, it's not forced to pick unnecessary controllers. And then it's also at the end, I think, because we're running the policy reactively, like I forgot how many hertz this is, but every once in a while, it's not like committed to like one set of controllers. So it can, depending on the scenario, it can definitely choose different controllers to get it out of these local minimum.
Right. So the first two ones, does that in any way contribute to incompleteness, in the sense that the inability to achieve certain tasks that actually do require the controllers to be combined in a way that now they're not in a null space with one another?
I think, I mean, yeah, if you only uses the controllers that we provide, it's definitely incomplete in that sense. Like it's not as flexible as just directly operating in join or end effector space. I think you can mitigate that in theory just by adding another, essentially like a very flexible, like robot-centric controller. So you can choose to do those robot-centric, say, for example, delta end effector pose actions. But I think, I don't know how much, I think this depends on the task, like how much value that adds for that particular task.
Right. Okay, so for the second one, I guess I wasn't completely sure the effects themselves during like planning. Those are being learned, or those are being forward simulated using like a physics-based simulator or something?
Yeah, so neither. So basically, during the parameter generation here, that gives us delta poses for the objects, and it's the skills are just trying to move the objects into those delta poses, and that's what the effects here are. So basically, if the preconditions are satisfied, we just say the object is going to be at that delta pose.
I see. Okay, so like typically, I guess would be good to understand uncertainty in the in those skills being applicable. So I understand that you can do have probabilistic preconditions and so on, but then there is also a question, kind of a more in the sense of confidence that you have in the prediction of the outcomes of those skills. Is that something that you think is feasible to achieve? Or?
Yeah, so there's one thing which is obviously the output of the precondition is a continuous number. We could calibrate that number and turn that into a probability, and that can allow us to incorporate that uncertainty into our planning method. In theory, I think that's great, but I think for this particular domain, the problem was that this effect is not as accurate as like perhaps like if you actually simulate it, would be much more accurate. So that means like if we don't, there's not too much benefits to planning like many steps ahead, basically, because the transition model is not very accurate. And this also makes it a little hard to evaluate like what's the benefit of actually incorporating the uncertainties in the preconditions, just because the effects are inaccurate. And I think in practice, what you can do for us, I think it's making the let me just see if I get this right. Making so instead of cutting off the precondition at 0.5, you can lower the number a little bit. So like we're okay with false positives, because if the object doesn't end up where it goes, we just do replanning. Yeah, that makes things a bit more easier to do.
Mm-hmm. So I guess does it kind of make sense to separate here the uncertainty in the data versus uncertainty in the model, so that you can actually reason about confidence in the predictions and plan, taking those into account, so that you can kind of find the plans that try to avoid try to avoid the actions that you don't have confidence in their prediction, which is different from just uncertainty in the outcome.
Yeah, I think so. One thing what you can do is that we tried this, but it didn't go too far with it. But I think one thing you can do is, instead of labeling whether, like when you're collecting your training data, instead of labeling an action as success or failure just by executing that action, you can actually sample like a region of actions around the initial actions and execute all of them. So that gives you a more robust label, so to speak. And that can capture some of the uncertainties with the action or with the perception modeling itself. And then you can use that information to help you plan more robust plans.
Last question about the last work. So, you know, in the kind of interactions with a robot via NLP, it's often useful to have information gathering actions, which would help you kind of better understand what the and so on. Do you see that kind of here, and how would that manifest itself? You know, like is that something that would also translate into certain robot actions, or is it purely just a verbal conversation?
Yeah, that's something we didn't demonstrate, but I think it's definitely possible. So one API that I didn't get to show in this work is there's like we call it like a say API, which basically just like it gives you call it with like a natural language sentence, and then it will play it on a speaker, and then you can converse with a human. You can definitely prompt the language model to ask clarifying questions when it is not confident. Or when it doesn't have sufficient information, you can say like put the block on the blue bowl or something, and they can ask you something like, which block did you mean? I think that's definitely possible. Yeah, I think you just have to add that to the prompt. But again, it's like if you just do things with the prompt right now, it is hard to give any guarantees on how like robust the system is. It's always going to ask the right questions. So I think it definitely needs some perhaps external memory or external data to record and reason about these things. But I think that will make a performance a little bit better, because right now in the prompt, the language model has never seen a case where it needs to ask clarifying questions when it's not sure. So right now, if you give it a vague command, it will just try to do something with it. It won't pause, it won't stop, or it won't ask for clarification. So you do have to show the language model how to do that in the prompt.
Right. All right. Yeah. Thank you. Thank you very much.
Correct.
All right, a couple questions from me. So the second project looked at sort of preconditions for these hybrid controllers or hybrid skills, and then the first one looked at sort of this idea of decomposing kind of skills. And would it be possible to actually learn preconditions for individual controllers before you compose them?
Yeah, I think that's definitely possible. Let me find a slide here. Yeah, that's definitely possible. I think the question is, how do we want to collect data for that? How do we want to collect? Like basically, if you're always executing the composed controllers, how do you assign like which controller was successful or not to the individual controllers? That's an interesting question. One potential way you could do that is, we didn't carry this out all the way in this project, but you could parameterize each controller and feed that as part of the input. So right now the input doesn't actually have the list of controllers, right? It's just the output is like a list of, it's like a multi-class classification problem for the output is like 1 or 0s. You could give, you could parameterize each controllers, give use some features to describe each controllers, put that as part of your input. So now you can actually do something interesting with that, like in an RL setting, if you're learning like a value function, if part of your input is the controller feature, that could allow you to extract some preconditions for individual controllers, just because now that's part of the input. That might be one way to do it.
So you obviously done some really great work, but someone once told me, a very wise person, that in research, it's always good to have a certain failure rate, right? So not all projects are going to work out. So I was wondering if you could talk a little bit about maybe some of the projects that you've done that didn't work out.
Yeah, I think the first project I did definitely didn't work out. It's not on the slide. But at the time we were trying to do this learning interactive perception for like articulated objects. Some of you might notice is the door handle project. We bought a lot of door handles for that project and trying to do these real world exploration with it. But I think especially in robotics, what's interesting is a lot of times the thing that bottlenecks you, or the thing that you spend most time on has nothing to do with the thing that you actually care about. And it was definitely the case for that project, where the bottleneck turned out to really be on the perception side of like robustly perceiving these metallic objects and getting these the depth or 3D information from these settings. Right nowadays we have better tools to do that. At the time it wasn't clear, and I wasn't doing perception research, so that's why that project didn't go anywhere. But I think in general I think it's good to basically just whatever project I'm working on is trying to do like the fastest, simplest thing that can give me some feedback signal whether or not this is a reasonable thing to do, and not worry too much about like the bigger systems until I get that signal. I think that helps to prune out a lot of failures much faster.
And I mean, so the focus is obviously, learning with extra priors. Are there any sort of priors that you see that robotics would benefit from that we've kind of underexplored a lot?
That's a very good question. Yeah. I think one question I like to think about is if we have simulations where you have ground truth information for pretty much everything, why don't we have an algorithm that just solves tasks with ground truth simulation? I mean, I guess you could argue that if you run RL long enough, it might solve that task, but do it in a more reasonable way. So I think there's a lot of prior knowledge that we can probably incorporate to answer that question, and that might tell us about where to go. Some things are like maybe, I don't know, better ways to reason about contact mode transitions is one of them, because you get no information just exploring free space, but you get a lot of information once you make contact, and how do you actually do this jump across different modes. That's something that's really hard for like gradient based optimization methods. Yeah, I mean, other things are also right now is just, I think we're limiting ourselves a lot just to manipulating with just the end effectors. A lot of these tasks would be easier if you are allowed to use the rest of the robot embodiment. And that actually might be a hardware issue, because I think the way we design robots nowadays don't really care about interactions with the rest of the robot arm, right? There's always stored in these weird geometries. There's no good APIs to deal with manipulation with the rest of the embodiment. So I think that's something that should be worked on.
Are there any other questions from the committee before we open it up to the general questions? All right, so questions either from online or from the room.
I have one question.
Yeah, go for it.
So Jacky, I mean, language is great, right? We have a lot of language, and that's how we use it. But like, if you look at it from a philosophical perspective, evolution did not have that, right? And yet we evolved, or like even other animals evolved to do like amazing things. So like, do you think there is this sort of disconnect between, like relying largely on this kind of like language or code, which, like evolution did not have access to, and like focusing more on the other aspect, or like, do you think there's a synergy between or something like that? Like, what do you think is the answer or the direction that we should go to?
Yeah, I think the practical answer is just we have language data, and that's why language is successful. If we had data about all these other things, I think they would be pretty successful as well, but it's really hard to get that data of how like agents interacting with the physical world.
But isn't like simulations like sure we have,
But yeah, exactly. So simulation gives you a cheap way to collect that data, but it doesn't tell you how to collect that data, right? Like you still need either some RL exploration, for example, or human demonstrations, and that's where the source of that data comes from. If you just do random exploration and simulation, I mean, I think you'd agree, like it's very hard to get meaningful data out of that.
But like from so sure, but like, do you think that will the code approach scale better versus this approach scale better, right? Like it's all about scale, right? Like this is all about scale.
Yeah, I think eventually one thing I might see happening is that we're bootstrapping, we can bootstrap from these other modalities that actually give us easy data. So text to image, text to audio, text to video. Basically what you can do is, I mean, I don't think we're there yet, but I do think in the next few years it's probably possible. Basically, like for example, how to perform like a task, right? You have a string of that task, you generate a video of doing that, And then you can do some real to sim from that video, like use some nerve to extract object geometries, or even do nerve-based simulations, get that into the simulator. And now you can use like these text to video, text to motion models to help you guide exploration, either as like a reward function or provide like infeasible demonstrations, but it's a way to guide exploration in simulation. And that's how you can get like bootstrap off of more readily available data to more scalably generate interaction data.
Great talk. So, when you like think about secant style planning, right? That's doing planning with very static skills. And then you have your work with code as policies where you kind of gone all the way down to writing direct code, which allows you to get much more fine parameterization on skills. Do you think there's something in between where you could parameterize skills with natural language using adjectives or adverbs to modify your skills more granularity than we've seen before, but you don't have to go all the way down to the writing code level?
Yeah, definitely. Like for example, you can use clipboard, right? For example, as like the low level policy where it just takes in more specific natural language instructions. I can do something like that. I think we've also seen some really great work from Google. It was like the 2D board domain where you can basically just speak to the robot and it will is still like an imitation learning setting. Basically the robot did a bunch of random actions and you can label these with natural language and just do some sort of imitation learning from language to the actual robot actions. I think that's pretty promising way to go, just because we've seen so many successes with text to something generative models. You can see like borrowing those techniques to these more like low level, more constrained action spaces, and then have a high level like secant type style planner to just orchestrating these more low level language condition policies. I think that's also very possible.
Do you think that would help mitigate some of the limitations you highlighted with code as policies where you can't prompt too much, otherwise you forget stuff, so it might limit your ability to do long horizon complex tasks?
Yeah, I think complexity it would help again because for example, I mean it's the same example I gave Sharon earlier. Is there are things that or models do or computers do that is just not written in code, right? Like object recognition is one of them. Like more dexterous manipulation, for example, like that's not, nobody has written that, right? It's all learned these days. So having a way to interact with that with natural language would be very helpful for more complex tasks. I don't know if that solves for long horizon tasks in particular, because like it doesn't have to. I think for long horizon or like lifelong learning, lifelong planning, I think you really need like an external memory to store everything instead of putting everything in the prompt.
Okay, cool, thank you.
Yep.
Any other questions?
I have one question. So like you train using data, right? And then is there any way to understand the control law like that you get out of the data and then use that controller as a prior for a new robot, like so that it doesn't have to retrain again from the scratch or something?
Is there a specific, like, are we talking about the first word or
No, I mean talking in general,
Okay.
like in all the work we basically use data to train particular kind of a robot. Now we have a controller that's like we can't see, it's a black box.
Right.
So is there a way to understand that controller and so that next time we have a robot, we know about the controller and we can like do some fine tuning on it, but not like learn from scratch again?
Yeah, I think that's something a lot of people are very interested in right now. It's more of like I guess this like foundation model type of idea for robotics. Like if you just train one model that has a lot of base behaviors, can you just use it like the way we use language models on new tasks, like basically prompt it or very little amount of fine tuning, get it on new tasks. It's probably possible. It is hard because the way these prompting things work is because you have a very rich description of the things that you want to generate and how your task is described. Like we do it with natural language, we have a lot of language-based data. What you really need, you should just train a model that just conditions on not language, just like robot behaviors, for example, or some abstract embedding of a task. We don't really have the same scale of data for those. So you, at the end of the day, I think a lot of successes is because it's not doing video generation, it's doing text to video generation. That's where the success is coming from, because text is so rich and expressive. We can leverage that for generalization. I think you would have to do something similar for robots too, if you want to do something like the way we use large language models, like text to robot control, or text to maybe some optimization problem, or text to some specification for the actual task. That was probably easier to do than just doing like something that's not conditioned on text.
Right. Also, it has a condition on itself, the robot itself, like what kind of hand it's using.
Yeah, and I think that's interesting, because I don't think people actually write that down in text, right? Like my finger is this dimension or something. Grounding can come from simulation, so it could use code as policies or something like that to like directly interact with simulation and get feedback. It can also come from just like if you have some way to describe the robot, like a URDF, maybe it can write code to parse that. We didn't put this on the paper, but we did find the ability to like generate code that parses URDFs, like changing all the mass of all the objects, or all the links, or changing the drawing configurations, or computing Jacobians from URDFs. So we can do that. So maybe that's another way you can get like this cross embodiment ability.
Yeah, thank you.
Any other questions?
So, how far, what do you think is our timeline for having natural language guide robots in the real world?
Whatever I say is going to be wrong.
Say anything in public.
Yeah, I think you have. I think two problems. One is grounding, and one is guarantees. If you don't have measurable progress on these two things, we're going to be stuck in research land for a while. And I'm hoping the language community can get some good results on guarantees, or just more empirical testing methods for these large language models. We'll definitely have that sooner than later, because a lot of companies are trying to deploy large language models. But there's a reason why, like Alexa, Siri, or Google Assistant, this is all scripted. It's nothing on here is learned, right? It's not running large language models, because it's very hard to predict what their outputs are going to be. But I think these companies have an incentive to invest in that and put more research efforts in that, because they do want to put this in products. And I think we can build on top of that progress when they do.
All righty, I think we're gonna wrap up there. So first of all, thank you again. This is the point where we ask everyone to step out, including Jacky.
I will just leave Zoom.
So if you could stop the recording for a second.
Okay, yeah.
Maybe I also have it here, my laptop. But we can use yours, but I think we need to keep everyone else out, because I don't know.